Hi folks, this is tutorial number 9 in the playlist that deals with doing buckling problems in 3D Experience. I consider this thing as a transitioning video in a sense that it's intended for people who are either entirely new to 3D Experience or they're ABAQUS users and would like to uh, consider the possibility of transitioning to the 3D Experience's FEA solver, which incidentally is ABAQUS. So the strategy for doing these videos is finding things that are done on YouTube entirely in the ABAQUS CAE and replicating the steps uh, to show you how different things are in the 3D Experiences interface, which I consider to be night and day, basically. All right, so the problem that I'm going to be doing is taken out of the website of this professor in England, and he is looking at a long hollow section with the cross section is actually a square. Okay, so it's a tube basically with a square cross section, and uh, he has done this problem entirely in the ABAQUS CAE program using static Riks approach because it's more than finding the buckling load. You want to see essentially uh, the nonlinear buckling problem. Uh, Now, the left side of this is pinned, and the right side is pinned on a roller, which means basically I'm dealing with a simply supported problem. And the kind of boundary conditions that I have to apply to the left side being a pin, but freely rotating about the y-axis is shown here. And because this is on a roller, it has the ability to move in the x direction. So that's free, but it can still rotate about the y-axis. And the way I'm going to do this problem is create some reference point at the two ends and create coupling between those reference points and the appropriate edges of the tube. Uh, the problem will involve three steps. The first step is a buckling analysis to find the theoretical linear buckling load, which is buckling load factor essentially, and that's done by applying a 1 Newton here, for example, and asking the program to give you the load factor. And then once I have that load factor, I will actually apply that load factor and let this thing deform. Of course, it's going to buckle below that load factor, and that's where nonlinearity is going to be taken into account, of course. Now, the data taken from the professor in England is coming from that paper, and it's the third row of this table. This is an ASCE paper, American Society of Civil Engineers, and some information is given there. For example, the Young's modulus and Poisson ratio, obviously, and then the yield strength and another strength and the corresponding plastic strain. So we're going to be using this data. The cross section's dimensions are shown here, but it's not drawn to scale, of course. And uh, the length of the tube is roughly almost 1750 millimeter. And what I'm going to do is after I do the buckling, before I actually apply the buckling load, I will introduce try to replicate some imperfection. And by I do that by applying 1 millimeter to the middle section of this tube, making it bow out, okay? And once that is done in the static nonlinear static step, then I do nonlinear Riks step, okay? So here's the data coming from that table, and let's move on. Uh, in that reference, it's indicated that the surface that we're going to mesh with shell element is actually the bottom surface. So I have to make sure that the bottom surface is selected, and the thickness of the shell or the tube is 4.02 millimeter. But make sure that the bottom surface is selected here. Okay, and move on. So when I do buckling, I get an error message saying that there is not enough iteration iteration number is uh, given. So what I have to do is, once I get this message, I will go and then change the maximum iterations, which is by default 30. I'm going to change it to 100. And once I do that, then it will run. It will run, and it will give me a buckling load factor of, this is obviously linear buckling, 1.5, and the reference, YouTube reference gives 1.75. These are all e to the 6. But keep in mind that we don't have the same mesh, and there are some minor differences between the two. So under the circumstances, this is acceptable. Now, here's the difference between our meshes, because uh, these are S4R elements, each 20 millimeter long. Now, of course, mine is kind of at the corners. I don't have a nice curved transition like this, but it's take too much, I mean, some extra work in order to make it look like that, which I decided to ignore it. So here is the information for the buckling. This is the information for the linear static step, where I'm going to be introducing those the lateral force causing an imperfection, essentially bowing out. And then I do Riks step with these numbers, okay, and make sure that the maximum displacement of the right end is not more than 12 millimeter, because that's the stopping criteria. Otherwise, it keeps running. So even in this case, it will eventually bomb out, and that's okay. We'll get to that before it does. To create that bowing effect, I create a manual group in the middle section, okay? And then to that group, I apply a constant translation of 1 millimeter, okay? And then this, of course, has to be removed. This particular translation has to be removed when I go and do the things in the Riks step. So here's the whole setup here. This is the buckling step. Nothing is transferred to the step 1, which is static step. And then when I go to static uh, Riks, Riks step, then I remove. Notice that this is removed. This is the translation that's removed. But and the load that I'm applying in here is that value of uh, I think I'm missing the force there. It should be 1.5 e to the 6, but we're gonna do that. Okay. Somehow when I took the screenshot, I had not applied the load at the right end. Okay, good. Yeah. So the data, the force deflection curve, the force deflection curve of that right endpoint when I'm pushing it is in the reference is given by this graph. What I generate is going to be something that's very similar to it, very close to it, as you can see. And when I do this, I get at some point the tube, the hollow section tube will actually look like this, which shows you that the buckling is taking place. And yeah, but this cannot be predicted, of course, with the linear buckling value, which is below that 1.5, which is below the 1.5 e to the 6 that I specified. Notice that here it's roughly 1 point, maybe 1.1. So the buckling is taking place at the lower value than what the Euler buckling formula basically gives. All right, so we are ready to start. Now here's the 3DEXPERIENC interface. I'm in generative shape design, of CATIA because I'm going to generate a surface. And let me do the following. On that vertical plane, I will sketch. I'll sketch a centered rectangle, and I will dimension these. This is going to be 100. And this is also going to be 100. Let me check that. Let's go back here. Yeah. Okay, now I want to put fillets at these ends. So one way I can do that is select this whole thing and then go to the fillet icon, and it will put it for me, and I have to put the proper value, which is going to be 8.6. Or I could have done it one by one. 8.6 millimeter. There we are. Exit. So here is my section, and then I will extrude it to get the surface. I will extrude it. By 1750. But the way I'm going to do that, I'm going to go to the left by 875 and to the right by 875. So let me put half of that distance there, 875. Remember, 875 times 2 is 1750. But I'm going to use the symmetrical extrusion. So it goes in both directions, and the total length is going to be 1750. And the reason I did it like this, I could have done it in one direction if I wanted to, but the reason I did it like this is because later on when I create a group of element here to cause that imperfection, I know exactly where it is. It's right in the middle. But let me change the the view here. So I don't want to see these hidden lines. There, maybe. Okay, that's good. I would like to see these lines actually, some of them, not the hidden ones. Let me see which one it is. Probably that one is that one there. Okay, so good. Okay, there's my section. Okay, why don't I also create my 2 points at the two extremes, because that's where the coupling is going to take place, and I'm going to put this thing right at the centroid of this end section. So, for example, under essential, a point, and one on this side. So 875, this was 875 plus 100. Oh, 875, so that's going to be 875. So that's going to be one reference point. You can see that. It's kind of hard to see it here. It's right there. Okay. And another one at minus 875. It's going to be at the other end, centroid of the other end. And you know what? I'm going to call these things right-click properties. I'll call this thing instead of point one, I'll call it uh, pinned. Okay. And this fellow, right-click properties, I'm going to say pin roller. That's the right end. Okay. Why don't we apply our material properties? So we go to tools, and find the place where it says create material or material browser right there. So create a material, and I'll call it SHS December 29, 2023. And of course, this is steel. Oops, steel, not SHS. SHS square hollow section. Say OK. Wait for this thing to pop up on our screen. Right there. Right click apply. And I can close that. Apply it to this fellow. And I'm going to input the material properties now. So expand this thing. All right. So it's structural, ABAQUS multiphysics, mechanical, elasticity. For elastic properties, I put down what we had was 211,000 MPa. That was the Young's modulus, Poisson ratio 0.3. Okay, and then for plasticity, metal plasticity, plastic, and I put down the yield strength, which was 787. This is high strength steel, 787.3. Plastic strain of 0. That means this is yield strength. And then 825.8, 825.8. And this is at plastic strain of 0.062, which means roughly 6%. All right, so that's good. Say fine. Oops, this should not be negative. Let me see now. Oops. Oh, God. Okay, right here, it should be positive, not negative. That's what the error message was. Okay, good. Let's do a quick save here. All right, so we're going to go to the measure, and the measure is done in this application, structural model creation. That's where the meshing is done. Empty FEM. Okay, and the mesh, and we're going to do a now if you see a lot of stuff at the bottom here, because many of these are now pinned. For example, I can find my meshing thing, but it's going to be I have to scroll this thing until I find it. So what I'm going to do instead is the following. I'm going to unpin these things so that I don't see them. Connection, unpin it, and unpin it. Mesh, right there. There is your surface quad mesh. You click on it, you select this, and then 20 millimeter. That's what we agreed on. And also, if you go to this icon here, edit all parameters. Why don't we make it quads only? Okay, not quad dominated, but quads only. Linear, of course. And we say, yeah, okay. And good. Okay, so it's right there. It's already meshed. Now, if you want to, oops, yeah, if you want to see the mesh, I just clicked on that, or I could have updated it also. I could have updated it here, or I just did mesh and it showed it to me. Okay, good. Now, we can in fact hide hide the part because right now the mesh and the part are showing, but that's okay. Let me actually hide the mesh. So right click, I do a mesh visualization, a mesh visibility manager, and I'm going to say don't show me the finite element model, just show me the part. Now why I did that is that because I want to create my coupling. So we go to well, actually, before I do that, let me apply the properties of the shell. So on the properties, shell, that is the uh, that is the uh, extrude that we're going to mesh. And sorry, we already meshed it. We're going to put properties on it, and the thickness was 4.02, 4.02, and I told you that we want to select the bottom surface. So notice that I expanded this advanced, and then down here offset definition, we want to select the bottom surface. That means that it's going to go inward. Okay, this is the outer face, outer surface, and it's going to go inward by 4.02, and we say okay. So we already have created our shell section here. Now we go to connections, and under coupling, first of all, name I'm going to call this thing fixed end coupling. Fixed end fixed end coupling. It's easier if you give it meaningful names, easier to debug your stuff. For the support, I have to select these eight edges. Okay, so let me see now. So we start here. The order doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8. And for the support, it's going to be that point that I created, which you can select it from uh, from the tree. I'm pretty sure if I had not created the tree, it would have taken the centroid of that point, centroid of that section, which would have been the same thing. So pinned, okay, pinned, yeah. And then for kinematic, for coupling, this is very important. This is very important, and I've mentioned that in tutorial 8. It has to be kinematic, and all degrees of freedom are coupled. Kinematic, all degrees of freedom are coupled. Okay, good. There we are. Now we do exactly the same thing on the other side. This is a very important step, which I forgot to mention that in the slides, but I've done it in slides in videos 7 and 8. So another coupling. Name I'm going to call the pin roller, pin roller coupling, any name that you want to give it. And for the support one, I'll select these eight edges. 1, 2, 3, 4, 5, 6, 7, 8. And for the support 2, I'm going to use the pin roller right there. As I said, if you don't do that, if you don't create a point, probably it will take the centroid anyways. But make sure that you do also kinematic, coupling type, and all of these are checked. Remember, these have nothing to do with degrees boundary condition. All it says is that the stuff on these edges are associated with that point, and all degrees of freedom match like that. In other words, whatever degree of freedom is uh, at these edges is the same as degree of freedom here. Okay, we say fine. All right, now if you want to see this, this fine is created, but in case you say update, it shows you to all the nodes, all those attachment rigid bar elements to those nodes. And if you don't see it, that's because I've hidden the mesh right there. Okay, you can see that right there. Good. Let's move on. Why don't we do a quick save here? Now, what I want to do is also I want to create my group of elements at this middle piece. Right now I don't need it, but when it goes to a static step, I will need those. So I'm going to say, first of all, show me the elements. Don't show me the part. I don't want to see the part. Good. And I want to create my nodes in the middle, exactly in the middle. The problem is that if you say don't show me the part, then it will not show you those planes either. So let me say, show me the part, I know where it is. But the view, I'm going to look at the view from the front. So view from the top. How about front or the top? It doesn't matter. So, okay, let me say front. Oh, no, sorry, side, right or left, or top, the front. The front is not going to be very useful. What do I have here? Not the front. Left, for example, or the right. You can see that. So what I want to do is I want to create all these nodes here, and I go to group, and the way I'm going to do that group by spatial group. So I'm going to say uh, spatial group right there. You can see that spatial group, and I'm going to use a box, and I'm going to put the cursor here and drag it so that it encloses those nodes in the middle. Click on it. A box is created, but this box is not big enough on the other side, so I have to drag this thing down to make the box. This, yeah, makes the box bigger so that it collects all those nodes in the middle, and now it does. You can see that. So I did create a spatial group one, and I'm going to call this thing actually mid span. How about that? Mid span, just so that I remember what it is. Mid span, spatial group one. Say fine. Good. So a group has been created here. You can see that this is the name that I give it. Fine. Now, as far as this one is concerned, we're going to save this. And we're going to go to the structural scenario creation. Our first step is going to be buckling. Yeah, first step is going to be buckling. So first of all, it is a structural problem you're doing, and the finite element is the one that we selected. Say OK. Just give it a minute. All right, good. So notice that uh, scenario has been created, but there's an exclamation mark here saying that no procedure exists. So I go to procedure, and the first one is going to be buckle step right there. You click on it, and remember this number, I said I'm going to change it to 100, because if I don't, it's going to come back and give me a warning, an error message actually. Okay. So you can probably go lower than that, but the default is 30. 30 did not get me anywhere, gave me an error message, so I just changed that thing to 100. You say okay, good. Now, notice that I can go and check the type of my element as soon as I created that procedure. The element type was set. I go double click on it. It says that the element type is S4, but I want S4R, so I change that. All right. And let's apply a boundary condition. So uh, what is that? Boundary condition. I remember there's a lot of stuff here that I don't want, so I'm going to unpin that and unpin the view and unpin the load. And when I say boundary conditions, then just give me the stuff related to this immediately. Okay, so I go here and I say fixed displacement. And this is going to be, I'm going to call it fixed for my own reference. I'll call it pinned end, pinned end. Okay. Now, uh, the different ways of doing this thing, for example, notice that here I can go and maybe try finding those connection, engineering connection here. This is a fixed end, pinned end, okay? I can select it from here, or I can go there and I say, hey, show it to me by connections. And I already created the connections. It's right here, fixed end coupling. Double click on it, it goes there. And that is X, Y, Z are fixed. It can rotate about Y axis, but cannot rotate about X and Z. So I say, okay, that takes care of this end, okay? Now, I should be able to see my, let's check that. Oh yeah, actually, let me put this thing in the proper view because I think this is the fixed end. Let me put it in the uh, isometric view to properly orient that. Yeah, that's it. That was the fixed end. Okay, good. Now let's go back and do the same thing to the other one. So goes right here, and I call this thing pin roller, pin roller. That's the other end, and it's easier for me to go select it from there. So I say show it to me with connections, and it is going to be that guy, pin roller coupling. I could have selected it from here also. Now for that, it can move in the X direction, cannot move in Y, cannot move in Z, cannot rotate about X, and cannot rotate about Z. Okay? And then we say okay. So you can see that that end, the appropriate boundary condition has been applied. I also want to apply a 1 Newton reference load at that end. So we go to force, load, on the force. The support, once again, I can select it from here, connection. And it's going to be the one that's pin roller or from the tree, either one. Good. And in the direction X, 1 Newton. 1 Newton. Oops, 1 Newton. 1 Newton. Okay. So let's check that. Here, you see that? 1 Newton. And then we say, move this thing out of the way. We say, okay. We are ready to do the buckling. And first of all, I'm going to save this. Excellent. And now remember, I said that we can go ahead and do the other step, but it's better to check these things one at a time instead of doing everything and then adding the nonlinear static and then nonlinear Riks, etc. So let's do it one at a time. So that's pretty much it. We already saved it. So we go to simulate. If these are bothering me, I can unpin it. Then this guy pops up here. Let's do a quick model check. I'm sure that's going to be okay. Let's do a simulation check. That's going to be fine also. This is going to, once we run it, it's going to bow out. Remember, I asked for the default, which is 10 buckling load, but the only one really that we need is that first one. Okay, so that's pretty much done. And then finally simulate, which means run. And assuming that I didn't make any mistakes, then this is going to go upward or downward, of course. And the buckling load factor hopefully is going to be around 1.5. I told you that the reference, the YouTube reference, is 1.7, but the mesh is different and there may be minor differences that I might have ignored. There we are, 1.512 uh, mega Newton. Okay, good. So let me close that. And there we are. If you want to see the displacement, it's right there. Of course, these displacements are totally meaningless. Okay, so this is the load that I'm the buckling load factor that I'm going to use to do the Riks step. Okay, so incidentally, if you want to see the mesh also, what you can do, you can click on this and then third tab and say that show me the mesh also. One other thing I want to show you here, notice it says shell style, none. If I say show it to me as a thickness, and if you zoom in, you see, it shows you the thickness. And remember, I went inward and this goes inward also. Okay, it has, but that's what I asked. So we say fine. If you don't want to see it, just say none and say okay. Good. So the next step is to create that imperfection by pushing this original flat orientation or tube up by 1 millimeter. And I'm going to do that after I take a couple of minutes of break. Okay, so let me stop this thing. Okay, before I continue with the rest of the problem, I want to make a few comments about uh, what we got and how is it different from the YouTube reference. Now, in the YouTube reference, the value, this eigenvalue comes out to be slightly different. It's 1.75 e to the 6, but these are perfectly acceptable. There are some change differences. Among them, for example, are the fact that my mesh is coarser than the professor's mesh over here. There's a finer mesh around the span. That could make a difference. And so let's move on now. Remember, the next step is to if I go to the base step here, the next step is to create a nonlinear analysis using a static step where I take those nodes in the middle, the mid-span of the beam, and translate it up by 1 millimeter. Okay. Now, this, in a sense, produces some kind of a deformed shape, and that deformed shape is expected to replicate the imperfection in the long section. Okay, so let me close that. Let's go to the scenario. Let's go to the scenario because we want to create another step. Right now we are in results, so we go to scenario, and I create a procedure, and the procedure is a static step right there, static step. Click on it. Now the data that I'm going to use to do this is going to match what I have in the slide, which is right here. It's this one. So everything is the same except that the starting time, the dummy time is 0.1, and everything else is the same. 0.1 is the starting dummy time. All right. Everything else is the same. And then we say, okay. Now, notice what happened here. A static state has been created. This is my buckling step. I could have deleted this. I can delete this if I wanted to, okay? Or I can keep it, but the problem is that if I keep it every time I run, it also does this because the case is going to be run and this is in the case. That's fine. I'll leave it the way it is in case I ever needed that. The other thing is that because I had the buckling step as the first step, none of the boundary condition information and the load has been transferred here. Okay, now I have to do that again. So let's go ahead and try it. So for example, under boundary condition right there, we have the first of all fixed displacement, and that is done by the coupling on the left, which is, let's see now, you can get it from here. It's easy to see. Uh, Here, fixed end coupling, and all the translations are fixed, and all the rotation except rotation about y is fixed. Okay, let's do another one on the other side, or the other one on the other side, which means uh, another fixed displacement. And again, you can do this thing you can select these things from the tree, or you can select it from this pull down menu under connections. And there's two of them. We already used the top one. This is the pin roller end. There we are. And this can move in the X direction, therefore I just leave that blank. And it cannot rotate about Y, but other rotations are, oh, it can rotate about Y, the other rotations are fixed. Good. And this one Newton obviously is not transferred to that, and I don't want it to be transferred, just leave it the way it is. So then we're going to take this middle section and push it up by 1 millimeter. So the question is, how do we do this? So we go here under the fixed displacement expanded. Here it says apply translation. See that in this in the boundary condition uh, tab, you get all of these, and the first one is the one that we're using, and submenu has got a submenu in it. Apply translation. You select, and the easiest way is to go and do it by group. Remember, I called this thing. I gave it a name. In fact, if you go here, you can see what the name of that group was. I think I called it mid-span spatial group, right? So we go here, we said, oh, let's pick it by group. I can go and pick it from here, there's no problem, but I rather do it from this menu. So there you are, right there. See all those points in the middle? You can see that they light up. See this? Where is it? Right there. See they light up? Okay. So you select this, and then upward displacement of 1 millimeter in the direction Z. And notice that as soon as you do that, these arrows are created here, which shows you that we actually have a boundary condition, or yeah, displacement specified here. Now there's no load, no other load acting in this step. It's just to move this thing up. So let's quickly save this thing, and then I'm going to run it. First of all, let's do a model and scenario check. Hopefully I didn't forget anything. No problem there. And then there is the simulation check. I bet this is going to be fine. While this is running, I want to remind you that we could have done everything in the same run. In other words, we could have created the buckling and then static step that I'm doing right now, and then static Riks, and then make a whole run. But I decided to do that separately so that we could make sure everything is okay. All right, good. And now it's going to be running. So, see, it's going through the static step. It did the buckling also because I did not delete it. It's sitting there. Okay, good. So this is the base step. Let me close that. I don't want to see the base step. I want to see the step. This is the buckling one. It's still there. And if you want to see the static step, it's going to be right there. Now that is the initial increment, initial frame. But if you go further down, you can see that it actually is moving up. Now you might say, wait a minute, I don't see anything moving up. The reason is this. When I created this static step, the nonlinearity was checked by default. When the nonlinearity is checked, the scaling of the deformation is 1 by default. If you want to see this thing, then you go and change that. So let me go double click on this and go to the second tab. See, scale factor is 1. I didn't do that. It happened because it was a nonlinear problem, automatically set it to 1. If I make this thing 100 times bigger, let's see how it looks like. Say apply. Ah, you can see that. So this is 100 millimeter, right? Now, I'm going to put it back to 1. So basically what we have done, we have made a slight dent, gave this long SHS section a, a imperfection, basically. Okay, so let me put this thing back to 1 and say okay. Good. So we are done here. Let me do a quick save. Okay, I'm now in a position to insert my Riks static Riks step. So I go to the scenario, you know, call it if you're not there, to structural scenario creation, but I'm already there, so I don't have to go there. All right, and then I create a procedure, and the procedure is a static Riks. And for the data here, I input the stuff that I showed you on that slide, on this slide. So let me see, on this slide over here, okay? So the only thing is that for stopping criteria, let me actually try doing that. So this number is going to be 0.05, 0.05. This number is supposed to be 0.1, 0.1, and total arc length of 1, and include the nonlinear geometric effect. That's by default on. Now here, notice that I want to specify the stopping criteria, and don't worry about that. Just use the default. So it says translation. So we're going to select translation. It says what node. Okay, so I want to select a node. The problem is that it won't let me create a node here. So what I'm going to do temporarily, I'm going to say okay and come back to this window later on. You say okay. What I'm going to do is I'm going to create a group I called my node selected node, and then use it later on. So I'm going to say okay. Anything that I've done here so far is taken. So we go to, you have to create a group. In order to do that, we can go to the model, final model, okay? The same place that you created the other group. You can see that I already created a mid-span group, remember that? Okay, so here's the group, and I'm going to say manual group, and I will select this node and say when the displacement of this node later on is more than 12 millimeter, stop. So we say, and I'm going to give this thing a name, my selected node for stopping criteria. Okay, but I'll leave it the way it is. Fine. Now I'm going to go back to scenario. I'm going to go back to scenario. So this is where we were, and are we there? Sorry, I think we're right here. A long, yeah, that's a long square hollow section. Is that? Oh no, this one. Oh, wait a minute. I think this is the one that we're working on. Yeah, yeah, long. That's right. We're working on this a long section, a square hollow section. Okay, good. So this is where I created this new group. See that right there? So I go to standard, go to my scenario, I'm there. And notice that the static step, there's an exclamation mark here because we did not finish it. So if I double click on this, I go back there. Remember these numbers are changed? And I go to stopping criteria, translation. From here, I select a group, and the name of the group is that my selected node. So when my selected node's translation becomes more than 12 millimeter, stop. Okay, good. That's pretty much it. Now notice that the applied translation got moved from the static step into the Riks step. I don't want that. This should go. So put the cursor on it. Cancel. Put the cursor on it. Right click. Remove applied translation in static step 2. Or you can go here. You can go to the feature manager. And this translation that is right here, you can right click, remove in step 2. Either way. So if I remove it from here, it's going to be gone. Okay. And let's check that. Notice that in Rick's step, there is no translation. Good. The only thing is that we have to apply a load of 1.5. I'm going to use a load of 1. Round this up to 1.5 e to the 6 Newton. So I will go to the load, a force, right? There's a force, and I'm going to apply it to that coupling on the right side, the pin roller. Remember that? The pin roller. So we go to, we can go to connections, and we have this here, a pin roller coupling. That's this side. You can see that. And I put 1.5 e to the 6. I see it right there, and say OK. So that's all we need, because this load was not in the static step. We had to include it in here, okay? And the translation we removed. Now, before we go any further, let me do something here. Say right-click, feature manager, make sure everything is there. Yeah, you can see this is the force that I just put in there, 1.5 e to the 6. I took away the applied translation, and that's pretty much it. Every other boundary condition, the strengths at the ends are translated. Good. So let's go ahead and save this thing. And we will do a quick model check. So we go to simulate. Let me scroll this thing here. Where are simulate? Must be somewhere there, right here. Model and scenario check. No problem. Simulation check. I don't anticipate any problem either. And then we're going to make a run, and that run will be quite fast. So maybe 3 minutes, something like that. So I'm not going to cut the video. I'll just going to let it run in the real time. Okay. This is still doing the checking, simulation check. It's done. Okay, good. Close that, and now we're going to run it. So this will run the buckling. It will run the static analysis, and then it will run the static Riks. Okay. If I had deleted, for example, the buckling would not have affected my results, but I didn't. It's doing the static Riks now. Already did the static and the buckling, and this is quite fast. Wait for a second. Yep, done. And I'm going to close this once the results are extracted. There we are. Okay, so first of all, let's look at the deformation, but not the buckle step. I want the Riks step. Okay, Riks step. There we are. I want displacement. There we are. And notice that this is from the previous step, namely the introducing the deformation, introducing that bow into the static step. So that is where the step buckling is going to take place. You can see that. Oops, that's too much. Now keep in mind that the scale here is actually, if I turn this thing around, the scale here, if you double click on this thing, the scale I made is 100. If I make it, for example, 10, it's going to be less dramatic, so you can see what happened. And as I turn this thing around, you can actually see there something weird is happening right there. So this is what's going on. If you look at the stress distribution, one Mises stress distribution, for example, and you go further, so this is basically the way I generated these graphs. Now let me go ahead and generate the force deflection graph. So we don't need this. Okay, good. So we go to XY from field, select the node, and for the node I select the roller pin, the one that's moving in. So there is a a connection that I created, pin roller coupling. There is one. This is the one that I want, but not all the steps. I want only the Riks step, all frames in the Riks step. Okay, and I want the displacement. So let me get the template here, the displacement template, and I want translation, magnitude, and I say okay. So this is the displacement of that endpoint where the pin is against the arc length. So that's okay. We generate this graph. It's over here, right there. Let me deactivate that. Let me do another one, which is the force applied at that end. So do another XY plot from field. Select another node set, but that is the same thing, namely pin roller coupling. Pin roller coupling. And I don't want all frames. I want the frames from the static step. And the template is force. What is that? Reaction force. And I don't actually want reaction force. I want the CF, concentrated force, applied to that location. So we say okay, and the magnitude. So we say fine. There we are. And now this is force versus arc length. So I'm going to close that, deactivate this, and then we go to XY plot from expression. Click on f of x, click on combine, select the displacement from there. We already generated that. Select the force, and then we say okay. And that is this guy, which is fairly close to what the reference is producing. Anyway, so that's pretty much it. We did first the buckling, and then the static step to introduce a deformation, and finally, or imperfection, and finally the static Riks. Now remember, there are other ways of introducing deformation or imperfection into the problem, including manual keyword changes and things like that. But here I just apply a force and apply sideways force, in this case upward force, and put a dent, basically initial dent into the tube. That's pretty much it. Good luck.